Hey guys, Mr. Cozad here with a video lesson for you on continuity. Admittedly, this is my first video with some new technology, so bear with me if something breaks or it doesn't go right. This is literally the first one with the new technology, so I'm learning as I go. This lesson is designed for my in-class grade level calculus kids. You will have a notes packet that you'll go through as you watch this video. But if you've stumbled upon this video and you're not one of my students, first of all, welcome. Today's a great day to be live. I'm happy that you're here. You can use this video and go through the notes as needed. Just grab a notebook or a notepad, somewhere to write some things down, and you can write down some of these problems as we do them. Okay, so there's going to be a lot that happens in this video, and I will go a little bit more quickly than I do in a traditional classroom setting, but that's okay because you can pause, you can rewind, you can fast forward, you can definitely go through this video at your own speed. So if I do a problem or explain something that goes pretty quickly for you, just feel free to pause it, go back 15-30 seconds and see, listen to it again and see if it makes more sense the second time through. Okay, so here we go. We're going to jump right in, and today's topic is on continuity. Okay, and what I want you to think about when you think about continuity is I want you to think about drawing a graph and think as you slide your pen or pencil along that graph, is it smooth? Are there any holes? Is there any jumps that need to happen? If you can, every section of a graph that you can slide your pencil on without picking it up is considered continuous. So in calculus, the way that we define or test for continuity is there's a three-part continuity test. Okay, there's a three-part continuity test. So the three parts are this. It's pretty self-explanatory. So the three-part continuity test. Part one is you want to see, does the function at a particular value a exist? So it must be defined. So for example, if I'm asked to find the continuity or a test to see if there's continuity at x equals 1, for example, that would mean that f of 1 just literally has to exist. It means when you look at the graph or you look at the function, when you plug 1 in, you can do that. You're able to do that. Okay. The second thing that you're looking for is you want the limit as x approaches that same value, that same a value of this function to exist. Then, so yeah, basically that means that as you, whatever that a value that you select for part one of the three-part continuity test, that must, f of a must be defined, and then the limit as you approach that number must also exist. And then the third part is the limit as x approaches a of f of x must be the same thing as the value you got for f of a. So all that basically means is as you pick an x value, as you approach that x value from both sides, you should get the exact same value. So that limit should be the exact same value as how that function is defined at a. So this three-part continuity test might sound a little confusing at first, but once you see it in the context of some graphs and some problems, it's going to make a lot more sense as we go through this. Okay. So let's go to our first problem. So here is an example of a graph, and the first part says, where is the function discontinuous? Okay, well this is actually really easy because what we can do here is we can just slide our pen or pencil along this curve, and we're looking for the places where we have to pick our pen up to get to the next section. So if I start over here on the left, okay, I start down here and I'm cruising all the way till I get to x equals -1. When x equals -1, I have to jump all the way down here to this next section. And then I'm cruising up until I get x equals 1. And then when I hit x equals 1, I've got to jump up to the graph on this next part. So there are actually 2 points of discontinuity here. We would say that x equals -1 is a point of discontinuity, and x equals +1 is the second point of discontinuity, because again, those are the only x values on this graph where you have to jump to another section of the graph. You can't just slide your pen or pencil without picking it up. Okay, so then over what open intervals is it continuous? Okay, so that means on what intervals does this function that we have this graph of give us, is it a continuous function? Okay, so again, start from left to right. Well, we start at negative infinity, because if you look at this arrow down here, that tells us x values approach negative infinity. And remember, we didn't have our first problem until we ran into -1, okay? Now, then we jumped, so we're going to have multiple parts of our intervals here, so we're going to use unions, okay? So then we jump down to -1, and we go to +1. Now, there might be somebody asking the question, well, Cosette, this is a closed circle, so why didn't we use a bracket, okay? Because at this point, x equals -1, it's discontinuous. And we're asked here to find the intervals where it is continuous. So at x equals -1, that's still not continuous. So that's why we use a parenthesis instead of a bracket. Okay, and then the third interval that is continuous is from 1 to infinity. So there are 3 sections of this graph that are continuous and 2 points of discontinuity. Okay. So what we're going to look at next is we're going to look at the types of discontinuity, okay? So take a look at this graph and then take a look at these 4 x values, okay? So let's look at x equals 0. So if I go and I find where x equals 0, okay, that's this section right here, okay? So when x equals 0, okay, what we look for here is, number 1, is the function defined at x equals 0? And the answer is yes, the function is defined, be defined as 1. But then you can very clearly see from this graph that the limit does not exist, because as I approach x from the left-hand side and as I approach x from the right-hand side, I don't end at the same point. So the limit as x approaches 0 does not exist. Therefore, this is a point of discontinuity, okay? And so to determine what type of discontinuity you have, there's basically 2 types, okay? Type 1 is called removable, and type 2 is called non-removable. Removable continuity, okay, is when it's basically just a hole in the graph, okay? Non-removable continuity, discontinuity is when there's a jump that's taking place, okay? So as you can clearly see here, okay, this would be a non-removable discontinuity, because I'm making a jump from one section to another. Now, if you look at x equals 1, okay, for x equals 1, we do actually have a scenario where the limit exists, because as I approach from both sides, I approach the same value, but the problem here is the function is not defined when x equals 1. So this is still a point of discontinuity, again, because the function is not defined at x equals 1. But as you notice, if it were defined at x equals 1, this would be continuous. So this is actually what we call a removable point of discontinuity. It's removable because basically if you fill that little circle in, you would have it would be continuous at x equals 1. But because that hole is the only thing keeping me from being continuous, we call that a removable point of discontinuity. Okay? So if you look at x equals 3, x equals 3 fails every part of the 3-part continuity test. X equals 3 is not even defined for this function, and the limit does not exist. So you ask yourself the question, is this a jump or is this a hole? Because it's a jump, we would say it's non-removable. And then we move on to x equals 4. Okay? For x equals 4, the function is defined at x equals 4, okay? And the limit also exists, okay? So this is a tricky one. The limit exists and the function's defined. But again, to be continuous, the way the function's defined and the limit have to equal the same thing, and they clearly do not here. So this is an example of removable discontinuity, because if you just filled this little circle in right here, it would be continuous. It's just a hole in the graph, okay? All right, the next type of problem that you're going to see sometimes is you're going to be given a function and asked to determine all the points of discontinuity and to label each type of discontinuity, okay? So really what you have to have here is you have to have kind of a basic understanding of what some of these graphs look like. Okay, so this is one that you should know. This is a cubic function. It's x to the 3rd power. So what you should know about cubic functions is they generally take the shape of an S that goes up to the right if the lead coefficient is positive, okay? So if you think about a curve that looks like this, there typically are no holes or no issues on a curve like this. So sometimes you'll have the ability to say that there's no discontinuity. And again, the reason that I know that there's no discontinuity is you have to know what the shape of this graph looks like. Okay, generally speaking, with cubic functions, there are no strange things that happen on this graph. There's no holes, there's no asymptotes. We have a very straightforward graph that just continues in each direction forever. So there's actually no discontinuity on a problem like this. But then we get to a rational function like this, and we see that there will potentially be some issues here, okay? So rational functions are really, really important for you to know in calculus because they show up a lot. So in my class, we've actually practiced these already. So hopefully what you would see is let's factor the numerator, okay? The numerator is going to factor to x plus 1 times x minus 4 all over x plus 1 on the bottom. Now, I know that my students would see this, that we've got a factor of an x plus 1 and an x plus 1 on the bottom, so those are going to cancel. So what I have left over here is I have left over x minus 4. Okay? Now, when you cancel a factor on the top and the bottom of a rational function, that creates a hole. And here's how you find the coordinates of that hole. You take that factor that was canceled out and you set it equal to 0. So we get that x equals negative 1. And then what we do is we take x equals negative 1 and we plug that into x minus 4, whatever I had left over. So if I plug a negative 1 in right here, negative 1 minus 4 gives me negative 5. So my hole on this graph occurs at the point negative 1, negative 5. It occurs at the point negative 1, negative 5. So then if you thought about the graph of this function, okay, it's going to be the line x minus 4 with a hole at the point negative 1, 5. So if you look at that particular graph, you can see that it's not continuous because at this x value, at x equals negative 1, we don't jump. There's a hole in that graph. So we would say that x equals negative 1 is a point of discontinuity. And we would say more specifically, continuity. Sorry, spelling's hard. X equals negative 1 is a point of discontinuity. And we would say that more specifically, it is removable. That it's removable. Again, it's removable because if you just filled that little circle in, it would be continuous at that point. The limit exists, but the function is not defined. Okay, next one, another rational function. Like I said, these are going to show up a lot. So on this particular function, okay, we see that there's nothing that cancels out on the top and the bottom, but we have to remember that there's going to be some asymptotes that happen here, okay? And those asymptotes are going to occur. The vertical asymptote, we set 2x minus 1 equal to 0, and we solve. We get x equals 1/2. So that's the vertical asymptote is at x equals 1/2. So you know right away that x equals 1/2 is going to be a point of discontinuity. And I'm going to abbreviate that POD, if that's okay with you guys, a point of discontinuity. Okay? So then what we have to decide, is it removable or is it non-removable? Well, we kind of have to remember what the shape of this graph is going to look like. Okay? And there's a horizontal asymptote here at 3/2. Because this is the coefficients, the degree on the top is the same as on the bottom. So we divide the coefficients. And then you can plug in some test points or go to a graphing calculator, and you would see that the graph is going to look something like this. Okay. Now, as you can see from this graph, as you approach x equals 1/2 from the right side and you approach from the left side, that limit does not exist, and it's not just a hole. Okay, it's not just a hole. It's a jump, so this is what we would call non-removable. Remember, the only time it's removable is if you have a hole. Okay. Next problem. Again, another rational function that we'll look at. Okay. The first thing I would do here is I would rewrite the denominator, factor out an x, so you have x times x minus 1. Now here we actually have two x values, okay? We see that we can factor out an x on the bottom and the top, okay? So that particular x value is 0. And if you remember from a few problems ago, when you cancel out something on the top and the bottom, that's going to create a hole. And if you create a hole on the graph, that is what we will classify as a removable point of discontinuity, POD. Now the second point of discontinuity here is going to be at x equals 1, because that's going to be another asymptote. Okay, well, x equals 1 is going to be an asymptote. It's not a hole, so that is what we'd call non-removable. Remember, the only time you have removable discontinuity is when you have a hole in the graph. Any asymptotes are non-removable. Okay, here's another type of problem that you're going to see when you're talking about continuity. We'll be given a function and be told that x is not equal to 1 and that f of 1 is equal to 4. So basically, if we think about our three-part continuity test, the fact that they tell us that f of 1 equals 4 tells us that f of 1 is defined. Okay, it is defined. So now what we want to do is we want to see if the limit exists as x approaches 1. Okay, if it does, then what we can do here is we can check to see if that limit equals 4. If the limit equals 4 as x approaches 1, we can say that this is continuous. Okay, but as you can see pretty clearly from x minus 1, x equals 1 is going to be a point of discontinuity because x is not allowed to equal 1, and they tell us that here. Okay, as we look at this, okay, let's factor out the top. So we've got x plus 3 times x minus 1 on the top. And then we have x equals, x minus 1 in our denominator. So the x minus 1 on the top and the x minus 1 on the bottom cancel out. So what we have left over is we have x plus 3 left over. Okay? So now what we're going to do here is we are going to say that we're going to evaluate the limit as x approaches 1 of x plus 3. So the limit as x approaches 1 of x plus 3, actually we can do direct substitution and we see that it equals 4. Okay? So here's what we have. Remember the three-part test for continuity. We have f of 1 is defined. That's a check. We have f of 2. We have the limit as x approaches 1 of f of x is also defined. It equals 4. And then 3, we see that the function value and the limit value both are the same. So we actually pass all 3 points of the continuity test. So we would say that yes, x equals 1 is continuous. That was deceptive. Okay, that was deceptive. So this actually wasn't even a point of discontinuity. Okay, that was a little tricky. I'm glad we did that problem. Okay, that's one that you probably want to go back and look at again. Okay, so it actually passed all 3 of those the parts of the continuity test. So that's really that was a good problem. I like that one. Okay. Next. Okay, so sometimes you'll see problems that are set up like this. Okay, to where you'll have what's called a piecewise function. Okay. So piecewise functions are functions where you have multiple different parts that are defined on certain variables. Okay. So the way that you read this is you basically say that this is going to be 2x minus 1 for any x value that's less than or equal to 0. But for x values that are greater than 0, you use x squared minus 1. Okay? So one strategy here is you could try and draw a graph of this function. Okay? Or what you can do is you can go through your 3-part continuity test. Okay, so part 1, all the magic's going to happen around x equals 0 here. So we want to evaluate what does this function equal when f equals 0. So you look at the bounds on x, and you see when x equals 0, this is the part that you use on the top, because that's the part that includes 0 in its inequality. So I'm going to take 0, and I'm going to plug it in for 2x minus 1. So that'd be 2 times 0 minus 1. That gives me negative 1. So that function is defined. So the next thing that I want to do is I want to see, does the limit of each one of these exist, okay? And does it equal the same thing? So here's how we do that. We're going to test to see if 2x minus 1 equals x squared minus 1 for x equals 0. So that means we're going to plug 0 into each one of those and test to see if they give us the same value. So 2 times 0 minus 1 equals 0 squared minus 1. I get negative 1 equals negative 1. So that's the same thing. So that limit actually exists. So part 2, the limit as x approaches 0 exists. And part 3 of the 3-part continuity test is that f of 0 is the same thing as the limit as x approaches 0 of f of x. So since it passes all 3, we would say that this function is continuous. It's probably good to practice another one just like this, okay? So let's do that next. So here's another piecewise function, okay? Here's another piecewise function. Okay, so the 3-part continuity test, part 1 is to figure out, does f of 1 exist? Okay, so as you look at this, you see that yes, f of 1 does exist because x is allowed to be equal to 1 on the absolute value of x minus 3, so that's where you actually plug your 1 value in. So we have the absolute value of 1 minus 3 equals the absolute value of negative 2, which just equals positive 2, okay? So now here's what we do next. So the next part to test number 2 is we set each one of these equal to each other. 3x plus 2 equals the absolute value of x minus 3. And then we test this for x equals 1. So as I plug 1 into x that I see on both sides, I get negative 3 times 1 plus 2 equals 1 minus 3. Well, we already did the work here to see that the right side equals 2. And we can see pretty clearly that the left side is going to equal negative 1. Now, because those are not equal, we don't pass steps 2 and 3 of the vertical line test. I'm sorry, not the vertical line test. I'm crazy. We don't pass steps 2 and 3 on the 3-part continuity test. So we would say that this is discontinuous. At x equals 1. And because those limits are not equal, we would say that it's non-removable. It's not just a hole in the graph. The limits don't equal the same thing, so therefore it's a jump on the graph, okay? And if you were curious what this graph would look like, okay, you put kind of a critical point or a critical line here at x equals 1, okay? And everything to the right of x equals 1 is an absolute value graph, okay? And everything to the left of x equals 1 is a linear function that would look something like this, okay? So as you can see there is a jump that's happening from one to the other. So it's not just a removable discontinuity, it's non-removable because you have to make that jump, okay? Next problem, okay, same kind of deal, but sometimes you're going to see some trig, okay? So again, first thing you want to look for is, do you see is x allowed to equal 0? And it is, okay? So let's figure out what f of 0 equals. So I'm going to use the first part, 2x plus 1, again, because that's the one that has the or equal to in its inequality. So 2 times 0 plus 1 gives me 1. And then the next thing that we're going to do is we're going to set both sides or both parts of this piecewise function equal to each other. okay? So we have 2x plus 1 equals sine x, and we're going to test that for x equals 0. And again, what we're looking for is we're looking for both parts to be equal. Okay, we're looking for both parts to be equal. So over here we have 2 times 0 plus 1, and then we have the sine of 0. So 2 times 0 plus 1 is 1. Think unit circle, sine of 0 we know is 0. So those are not equal. So we would say that there is discontinuity at x equals 0. And again, because the limits do not equal each other, we would say that this is non-removable. Again, it's only removable when the limits are the same, the limit exists, but the function is not defined at that value. So this is non-removable. Okay. Next one, another trig equation. Here, we're going to approach this the same way, okay? But we actually don't have to get as far on this one, because if you look, this is a sneaky problem. If you look at the way this piecewise is defined, f of 0 is undefined. So if the function's not defined at 0, you automatically know that it's going to be discontinuous, okay? But we still need to check the limits to see if it's removable or non-removable, okay? So we have 2x plus 1 equals the cosine of x. And we're going to test that for x equals 0. So 2x plus 1 equals cosine of x, test that for x equals 0. We have 1 equals 1 as we do that. We get 1 on the left, 1 on the right. So those limits exist. They're the same thing. So we would say here that there's discontinuity at x equals 0, but this is actually removable because the limits exist, okay, but the function is undefined, okay? Now this is a kind of a fun problem here, because what we do here is we're going to actually set this up into two different parts. So we have, if you look over here, the way the piecewise is defined, we've got a few different values that are happening here, okay? All right, so the first thing I want to look at is I'm going to test this at x equals 1, and I see that f of 1 is defined, okay? I'm going to use the first little part here, 2x plus 1. So I plug a 1 in for x there, and I end up getting 3. So f of 1 is 3, okay? So then let's take those two parts, 2x plus 1, and set that equal to 3. And let's test that for x equals 1. Well, when I test that for x equals 1, I do get that 3 equals 3. So we see that the limits exist. We also see that the function exists. So we would say that we are continuous at x equals 1. Because, again, it's continuous because the limits exist, the function exists, and they equal the same thing. The limits and the function, the defined value, are the same thing. So we would say continuous at x equals 1. Now the next point we're going to evaluate is we're going to do 4, x equals 4. So we look to see, is f defined when x equals 4? And it is. We're going to use this value here. So that equals 3. So then what I'm going to do next is I'm going to set those two parts equal to each other. And I'm going to test this for x equals 3. Okay, so I have 3 on one side, and then I have negative 1 squared plus 3. So I end up getting 3 equals, let's see. So I get 3 equals, negative 1 squared is 1, 1 plus 3 is 4. Huh, so that's interesting. Actually, oh, whoops, you probably already were way confused on that. I don't know why I plugged in x equals 3. I should have plugged in x equals 4. My badness. It's getting past my bedtime, y'all. Yeah, if you looked at the top of the iPad, you'd see 8:05. That's when Cozad goes to bed. Yep, you will too when you're an old man. Okay, so here's where we're at. Sorry, my bad on that. So we plug in x equals 4, and we get 3 equals 0 squared plus 3
And looky there, we get 3 equals 3. So we see that the limit exists on both of them, and the limit value is the same as how the function was defined. So we would say that we are continuous at x equals 4. So that one we kind of split into two parts. Okay. Moving on. Okay, here's another one for you to try. You can go ahead and pause the video now and try this on your own. It's very, very similar to the one we just did. Okay, but you don't have to get super far on the continuity part, because as you look at this, you'll see that those functions are not defined for -2 and +1. So go ahead and pause the video here and see if you can figure out what types of discontinuity you're going to have at x equals -2 and x equals 1. Okay, hopefully you paused it and actually tried that. If not, you're either just really confused or you have stopped watching the video long ago. For those of you that are left, thank you for sticking with me. Okay, so again, let me explain why I know that there's discontinuity at -2. So I know that this is discontinuous at -2 because if you look, the function is not defined anywhere where x equals -2. There's no or equal to. So it's discontinuous at x equals -2. We just need to figure out what type of discontinuity. So to do that, I need to check the limits. So I'm going to take these two parts and I'm going to set them equal to each other for x equals -2. So I plug a -2 in for x. So -2 is +2 plus 1 gives me a 3 on the left-hand side. And then -2 squared is 4 minus 1 is 3. So the limits exist. The limit as x approaches -2 is 3. So because the limit exists, we would say that this is removable discontinuity. Okay, so now let's check it on the other side. So on the other side, we also know that it's discontinuous at x equals 1. Continuous at x equals 1 because, again, this function is not defined where x equals 1. So here's what we have. We have x squared minus 1 equals the square root of x minus 1 plus 2 for x equals 1. So we just plug and chug. Okay, plug a 1 in for x squared. That's 1 minus 1 gives me 0. And then the square root of 1 minus 1 is 0. 0 plus 2 is 2. So those are not equal. So the limit does not exist. Therefore, we call it non-removable discontinuity. Non-removable. Okay? All right, guys, we are almost done, I promise. Okay, thank you so much for sticking with me. I've got two more problems. Yeah, 2 more problems for us to do. Thank you so much for your patience. I know this is a lot of material. And I know we're going fast, but I'm sure you're doing a great job. Okay, so here's the next one. It says determine the value of a that will make the function continuous. So again, this is a different type of question. Okay, here, so essentially, the first thing we want to look at here is we want to say, okay, number one, does the function exist at x equals 1? And yes, it does. Okay, yes, it does. So we know the function exists, so in order to make this continuous, we need ax plus 2 and x squared minus 3 to be equal when x equals 1. So what we do is we still plug a 1 in for x, okay? But we solve for a so that this is equal. So we have 1 minus 3 is -2. Then we have a plus 2 on the left. So subtract 2 on both sides. We get a equals -4. If a equals -4, okay, this limit will exist. If a equals -4, this limit does exist, and it will be the same thing as f of 1, because if you plug that in, f of 1 equals 1 squared minus 3. It would equal -2, which is, again, the same as what our limit would equal if I used a equals -4. Okay? Now, the only thing that gets more complicated about problems like this is sometimes you actually introduce 2 variables. Okay? Sometimes we introduce 2 variables. So, again, we want to pick an a and a b value that will make the function continuous. Okay, so to do that, we're actually going to write 2 equations. So here we have x minus 1 equals ax plus b, okay? And we want to test that for x equals negative 1. All right, so plug a negative 1 in for x, and we get negative 2 equals negative 1 times a would be negative a plus b. Now, in order to figure out when you have two variables, you need two equations. So we're going to have to do a second equation. So here we take ax plus b and set that equal to 2x squared minus 5. But this time we're going to do x equals 2. So plug that in, you get 2a plus b on one side equals 2 squared is 4, 4 minus 2, or 4 times 2 is 8, 8 minus 5 is 3. So what we have now is we have a system of equations that we get to solve, okay? Y'all probably thought you were done with systems of equations, but we have negative a plus b equals negative 2, and then we have 2a plus b equals 3. Now, there are various different techniques that we can use to solve systems of equations, okay? Some of them are substitution or elimination. Those are the best ones. What I would do is I would probably do substitution. I would rewrite this equation as b equals a minus 2 by adding a to both sides. And then I would substitute that in the second equation. So anywhere I see a b, I would replace that with a minus 2. So if I clean this up, I get, that's a 2 there, I get 3a minus 2 equals 3. Add 2 to both sides, we get 3a equals 5. Divide both sides by 3, we get a equals 5/3. Okay, so now once I have a equals 5/3, I go back to this equation that I solved for b, and I plug that in. So I have 5/3 minus 2/3, or minus 2, which I can replace that with 6/3. 5/3 minus 6/3 is negative 1/3. So there's your a value, there is your b value. Man, I know that's a lot of material. I know it's a lot, okay? And again, I'm sorry there was so much, but this is really important for you to know. Big thing to remember, if you go all the way back to the beginning, the 3-part continuity test, okay? The 3-part continuity test. The way that what you're looking for is the function defined at that x value? And then you look, does the limit exist at that x value? And then if the way the function is defined equals a number, and then the limit equals that same number, that is what you're looking for to verify that you have continuity. Okay, so thank you so much for sticking with me. I'll see you next time.